Next presenter is Mr. Ambuj Gautam. He is from IIT Kanpur, and today he will be presenting on a topic called New Design of an Electromagnetic Transducer for Unidirectional Shear-horizontal wave. So I invite Mr. Ambuj to start your presentation. So the presentation duration is like 15 minutes, and then we'll have the question and answers.
Thank you, Anirudh. Thank you for introduction. Good evening, professors, the researchers from other part of the world, and colleagues of SMSS lab. So far we have talked about we have a lot of very genius researchers across the world, and they talk about the robotic and robot mechanism. So my main focus or my topic is related to the sensor part. Since I'm designing a new sensor which can work for the pipeline health monitoring system. So as we know that Professor Vishak Bhattacharya has developed a pipeline health monitoring robot, and I was also the part of that. And it contains various sensors along with that robot, and it can go inside the pipeline and inspect the health of the petroleum or gas pipelines. So along with that, there is another sensors which is required to work to need to install with that robot, and it can give a better like inspection data. So that is the ultrasonic based sensor. So in the introduction part, I must include the piezoelectric, since as we say that ultrasonic testing. So first terms comes in our mind is piezoelectric material or piezoelectric sensors. So the major disadvantage with the piezoelectric sensor is that it need always a coupling, and once your robot is moving inside the pipeline, there is always a clearance which we need to maintain. So we will lose the opportunity of using the ultrasonic sensors. So that is what the advantage comes to use as a EMAT, electromagnetic acoustic sensor, which can use as a lift off with the sensor and the object surface. So the basic principle behind the EMAT is it contains majorly two components. One is the coil, which is having the alternative current, and another is the static magnetic field. So under the alternative current over the surface, it generates the eddy current effect on the surface, and with the applied static magnetic field, it will be able to generate the Lorentz force on the surface, and this Lorentz force act as a body force, and it generate the elastic deformation, elastic displacement on the surface. Depending on the direction of the Lorentz force, it is very easy to generate kind of a variety of the wave propagations you can see. So here is a general formulation, like how the current with the help of the alternative current, eddy current effect is developed, and with the help of the static magnet, a Lorentz force is developed, and this Lorentz force as a working as a body force, and we can get a wave. We can able to generate a wave. So basic mechanism has only two. Most of the EMATs has two. One is the Lorentz based, another is the magnetostrictive. Lorentz is if the force is if the both eddy current effect and the like magnetic field both are mutually perpendicular, and then the Lorentz force will be acting mutually perpendicular to both. And if the eddy current effect and the magnetic field directions will be in the same direction, so in that case that whole sensor is work as a piezoelectric material, a piezomagnetic, that is known as a magnetostriction in some other say. So most of the conducting material is having effect of Lorentz force based detection, and those who are the ferromagnetic that can be used the magnetostrictive based emit. And here in the corner you can see this has been developed by me, and it is used for the bulk wave propagations. So basically bulk wave based sensors can be used to detect the thickness of your object testing. And the idea is to develop these sensors can be installed on a smart inspection robot on the periphery. And there is a two location. One is for the transmitter and another is for the receiver. So one can transmit, and the circumferential wave that surface wave can propagate over the pipe surface, and it can collected by the receiver. So based on the time duration or time to receive at the receiver is, we can calculate, we can able to localize the defect position. So this unidirectional wave propagation based emit sensor is especially designed for surface wave. And here is, I have taken one assumption, since most of the circumferential pipeline guided technique use the longitudinal mode or torsional mode or fracture mode. So fracture mode is more complex in the to analyze as a model. So I focus on the torsional mode. If the aspect ratio means the ratio of inner dia to the outer dia is greater than 0.5, then we can assume that circumferential shear wave mode in the pipe as a plate, as a shear horizontal wave on a plate. So this can reduce our complexity to solve our problem. So that is what this sensor is designed for the pipeline, but the calculation is done assuming a plate, and try to develop the sensor so that the propagation is in only one direction, either X or Y. So I have modeled this with the COMSOL simulation. So before modeling, we need to fix the exciting frequency, so that according to that we can design our coil and the magnetic and magnet geometry. So I have taken a material as aluminum. Although the pipe materials are different, just as a prototype, I take a material as aluminum, and I draw the dispersion curve. I use the Floquet boundary condition for this dispersion curve. So I found that the SH0 mode can be achieved. And another assumption is, as for the guided wave, the frequency should be low for the guided wave kind of a propagation. So I assume the wavelength is 16 mm, and as per this wavelength, the frequency for this emit is achieved around 196 kilohertz, so that we can obtain the SH0 mode. And now coming to the emit design part, it has a three-part: majorly coil, magnet, and impedance match. Impedance match is already the another part. So today I will talk about the coil and magnet. So the special design about this coil is, it is having a chevron sign structure kind of us. So it will able to generate a guided wave in unidirectional. So while seeing this, we can say here that it work as a spiral. It work, if you see the right side picture, where the current is flowing, it work as a spiral and the meander lane. So it has the combination of both. Here I have taken the wire dia is 0.2 mm. We can increase also, that will increase the eddy current effect, and the wire spacing is I have taken half of the wavelength, and the angle I have taken is 45 degrees, the Savran angle, and applied current I have chosen is 10 amperes. And similar fashion, instead of a single magnet, I have used as a PPM. PPM can be used with the period of half of the wavelength, and I use the grade of N50. We can also increase the grade up to N52, which will increase the magnetic field. And I have kept the lift off of 3 mm from the surface of our study. So coming to the study part, simulation study part, I analyze in the 3-step. One is for the static magnetic field, another is frequency domain analysis for the eddy current effect, and third is with the help of these two results, we can easily integrate with the solid mechanics interface, where we can able to achieve the Lorentz force. Here, I have taken the mesh size is the wavelength by 510, which is recommended use generally. And as a boundary, I have taken the sides of the plate is outer side of plate is PLM, perfectly matched layer, where wave can be go and it can. And the surface where the displacement can occur is it is skin depth. So that is also based on the magnetic permeability of the material and electric conductivity. So on this way, I just did experiment, and I found the eddy current is quite reasonable, and the magnetic field is also, as the sum is going downward and coming upward, and the over the plate I got vertical is 0.282 Tesla. And here is very interesting. You will find the proportional arrow is showing the proportional in magnitude. So all the directions of the magnetic force resultant direction is along the horizontal axis of the upper plate. And here, if I draw the Lorentz force along the y is equal to 0 axis, y is equal to 10 and y is equal to minus 10, you find the y direction displacement here, y direction displacement more. But the propagation, if you see, here also you see the y direction displacement is more compared to x direction, and displacement also you will see the y displacement in y direction is more compared to the x and z. But the wave propagation is only in x direction. So this means it is able to generate the Shear-horizontal wave. And this is also the contour plots. With contour, we can easily see there's a nice picture which is showing the wave propagation is unidirectional. Another way is to see the radiation pattern. Radiation pattern is very beautiful, and it shows that it is the propagation of the wave is unidirectional. I have compared with the two things. One is the various external applied current, and another with the lift-off. I reach up to the 1 mm lift-off of the coil, not with the magnet of the coil. Coil is the least surface of the coil, and I found that 0.7 mm lift-off with the of coil and surface is more favorable in terms of the displacement and other effects. Here also I just draw this. You can see the 0.75 mm liftoff is quite achievable with this much configuration of the sensors. Here also we can see the displacement. It is true that as we are close to the surface, we'll get a more displacement, but it is important to achieve the lift-off, and 0.7 mm with, if you want to increase the lift-off, we have to increase the power in terms of, we need to increase the eddy current effect and the magnetic field effect, which will enhance the body force, and that will be required. So with this, I can conclude that the designed EMET is very much favorable for developing the unidirectional wave propagation, and especially especially SH wave propagation, and it can be good with perform good with the 0.75 mm lift off from the object surface, and it can be also further developed for the more lift off condition with enhancing the power, eddy current effect and magnetic field. There's a trade-off. I just want to mention this part. There's a trade-off. We can't increase the more current because the wire diameter is less. So there's always trade-off the heat carrying capacity of the wire and whatever the current power is supplied. So we need to make a balance on that. And and that is all. Thank you. I request for your valuable comments and suggestions. Thank you.
Thank you, Mr. Ambuj, for that nice presentation. For the interest of time, we'll take one quick question and then we would move on to our keynote sessions. So, one question. Any questions from audience? Okay, so if you do have any question.
Yeah. Hi, Ambuj. What is the thickness you can go up to for thickness of the material you can scan up to?
Sir, actually, this unidirectional SH wave is generally for guided wave. So it always travel on the surface, no matter whether your part is thick or not. But in my case, I have taken the thickness of aluminum sheet is 4 mm. So it is also designed for only circumferential surface defect.
Okay, it's only for surface. Okay, thank you. Thank you very much.
Okay, so any more questions? If you do have some question, you can also type Mr. Ambuj in chat